topic of today, which is when is 3D printing not the best option and when does it make sense? Thought maybe Jesse, you want to start with this first?
Yes, absolutely. So we kind of emphasize there the not the best option, because there are lots of times when it's a great option, but not is something as especially now with companies being really forced to cut costs and reduce cycle times on designing the product from beginning to end. There is a lot of emphasis on, oh, we could 3D print this part. And while that may be a good solution, it also may not. And some of the things to consider are things that we think about in product development, like tolerances, like surface finish, like repeatability, and things that 3D printing, while it's gotten better over time, it still has some of those factors that are making it not the best choice. I think we show in this graphic here 3D printing or additive manufacturing on the left, and its emphasis is a good for unit volume from 1 to 50,000 kind of cost and so on. But we want to focus on that with cosmetics, you're going to need secondaries. Not okay with paint. If you're not okay with some kind of, let's call it less perfect cosmetics, not exactly the same every single time, then 3D printing might be a great solution. But if you need to have those, say, the color or the texture molded into the part, then you really can't consider 3D printing. So it might be a good thing to consider, but not for production. Then cycle time. 3D printing is great for getting out quick parts. No tooling required. You can often make a lot of design, let's say, shortcuts in a way. You can have thick sections. You don't have to worry about consistent wall thickness and so on. So you can get your design out fast, but we all know that you can print a lot of parts, but not as many as with injection molding. So yes, you can get parts out quickly. There's zero tooling cost, but can you make hundreds of parts in 2 weeks, like you can with a multi-cavity injection mold, for example. So those kinds of quantities and lead time, when you graph them together, I think we'll show that a little bit later. You'll see that there's some times where additive manufacturing doesn't quite stack up as well as injection molding. Mm-hmm. Those are just a few examples. David, do you have any other thoughts or input on that?
Yeah, I see a lot of this being blended together, especially as we start to people get more used to additive manufacturing materials and how those materials, although not identical to the injection molding material, they begin to correlate and understand how they relate to each other, that these transition points really start to blend together. And you really start seeing the value of additive when you can reduce the number of changes and go to market faster. And when you understand the material, that that's really the power of digitization, I think, and that's where people are really trying to go.
Agreed. Yeah, I think that's pretty good cover there on that.
Yeah. So in terms of the product life cycle, again, stemming from what we were just discussing, we see a lot. Additive manufacturing technologies tend to be used for your prototyping and ramp volumes. We're seeing them going over into your actual production, where this is going to be the part that, in economic cases, lower volumes today, is actually going to be used to make a saleable product that's going to go to, be sold to a customer. And then also over in your service and aftermarket area, there's some really complex analytics over there to determine if the material is actually going to work, and a lot of engineering that has to occur to validate that something's going to work. Typically in that area, you might not have the engineers to be able to prove it out. So I always caution people to make sure you have the right resources to be able to deploy that. And then as you move up, there's other technologies. It's like your aluminum injection molds. I personally love aluminum injection molds. You can cut them really fast. People sometimes do development and research work on aluminum injection molds, and really, if you have a very specific material or very specific material outcome that you're looking to use, it's a great solution. Up into steel injection molds when you get to higher volumes, or even lower volumes, but you have like really crisp shutoffs or something that you have to achieve like a fine dimension on. But really, where the value of additive is when you start to accelerate your time to market. So, and what this means is that as you go up this curve, like you're going up the curve faster, and you're also going up it sooner. So, and what we see that is like people that are gaining a competitive advantage is when they start to understand how those materials actually work, they can validate their designs faster, which enables things like functional prototyping. They reduce the cost of engineering changes, saving a lot of capital expenses. And really where the best value is when people take a systems approach and say, well, I have a high volume product. Let's say I'm minimizing my number of my platforms that I'm going to have, but I want to offer a bunch of SKU variations on that platform. So enabling a certain level of customization, your ability to leverage two different designs, you can get pretty smart and take those systems approaches to take additive manufacturing all the way to the top, in conjunction with injection molding technologies.
Great. Well, I think we have now, built on that foundation, we're going to talk about some real world applications.
Yeah.
David,
So
this
is probably my
yours?
favorite. Yeah. This is one of my favorite. This is the example that I like I said earlier. I'm an injection molding person. I've made my career building molds, and I've built about 1,500, all continents, all over the world. And when I realized the value of additive manufacturing, and really what it is additive manufacturing and multi-jet fusion specifically, is a flexible manufacturing platform. And in that platform, the way that you utilize that space and the way that you put parts inside of a flexible manufacturing place drives specific outcomes. So when I was developing one of our HP's 580 system, we ended up trying to prove out how are we going to additively manufacture things? And part of that strategy was determining that it's like, well, what kind of parts are we going to produce, and how are we going to produce them? This was really that first point on the financial curve where we could start illustrating value. And really what we did is got the engineers intimately involved with the placing and packing of parts, so that they were concerned about build orientations. They were concerned about how these parts were going to thermally basically be manufactured next to others. When I looked at this, I started looking and said, so in the example here, this is 80 parts. If I was to release 80 injection molds, now granted, I could release 80 family molds, or let's say 50 family molds, and that's still a lot of molds. And it's really difficult it's expensive, first off, expensive to release molds. At the lower end, you're probably $5,000. At the upper end, you're probably $25,000. If you're into steel, you're even higher than that. But we're talking that many molds takes a lot of money, and it takes a lot of time. And I have typically, I'm manufacturing engineer. I like to be at the mold trial. And if I'm going to run 80 molds, I'm going to say it's going to take me about a week to do, using multiple tool shops. And that doesn't even include the mold build time. So, you could have weeks and weeks of doing this with a flexible manufacturing platform. And once you have the designs done, within 24 hours, you can have sample parts and actually start getting early feedback. Whereas if the others, I have to deal with inventory, I have to deal with mold trials, probably have to take a flight to China. I mean, there's a lot of complexity here.
Agreed. And then this is also repeatable. You have an example here where we took these 80 parts and nested them. The picture on the left is a picture of a nested build in the multi-jet fusion process. And you could take that's called a Kanban build, where you take all of the parts and nest them together. You could take that and multiply it. You could set probably two more systems worth of parts on top of that one. And so then you could scale it, and you could print a significant quantity of parts in a usable material in a very short time.
Yeah.
So if your product volume is pretty low, that could end up being your production potentially. If it's not, then it's certainly a helpful ramp, as you showed in that last slide. It gets you usable parts quicker and gets you up into analysis faster, and helps you make that curve steeper and shorter. It's an incredibly powerful tool when used even in concert between 3D printing and the injection mold tooling.
Mm-hmm.
Yeah, great example. Okay, this is Jesse again. I'll speak about this. This is an interesting example to especially to this group as well, because we managed this project. We 3D printed it. What the product is Mapper is a company that makes add-on cameras for drones, and they need a bracket that holds the camera in place on the drone. So the part we make is the part that's pictured in the right. There's 6 of them shown there, kind of 5.5. That part is 3D printed in multi-jet fusion, and then it's dyed dark green. And so the picture on the left, you can see the green part that we're pointing to. It's the DJI Mavic Pro mount. This is something where this customer is low quantity. They need something like 20 or so of these a month. The design is changing, as we all know. Drones and camera pieces of electronics, they change very quickly. So the product life cycle is extremely short. The usability in the market is very short. So committing to tooling is very daunting. They're not going to be able to get their money back out of the tool, most likely. And they have a very complex design. And so once we manufactured this project and product, and I spoke with the owner of the company and asked him some questions about how he's using this technology. And you see up in the upper right there, it says traditional method, meaning injection tooling or machining, I guess we could say. He said it was not considered due to the geometry, pricing, lead time, inventory control, and future design flexibility. So basically, he was taking advantage of all these things that 3D printing brings to the space. And as we looked at it, we didn't want to say, oh, you can't make this with an injection mold, so no, we can't do your project. Instead, having the ability to 3D print allowed us to say yes. And then as he builds his demand for the product and sells more of them, then it may make sense at some point in the future to be able to jump into an injection mold tool. So it's a great way to kind of get him started on it, get him going, allow him to focus on his product function, not worry so much about whether one of these features is going to create the need for another slide or a lifter. It really made it something that he could really focus on the functionality of his part. And then as he goes forward, we've had another one that I just had a conversation yesterday with another client saying, I now have enough orders that I think I can justify an injection mold tool. And so since we've been along with them on the whole ride, then okay, that's an easy one to go in and analyze quickly and get a good quote for. So looking at this again, the advantage here, HP MJF additive with GoProto added flexibility for just-in-time inventory. So what he does is he orders, I said he needs something like 20 of them a month. He orders 5 or 6 of them at a time, or he might order an entire month and have it's very low inventory. He's located domestically, so shipping is extremely low cost. It makes it very low commitment, very low cost for him. Design flexibility, allowing for printing of parts not possible with conventional methods. So any of you that have made tools before, you can see that there's a lot of very complex angles on here. There's features that are kind of coming in from the side, holes in different places that would make for a very, very complex injection mold if it was even moldable at all. So you get this idea of kind of complexity for free with 3D printing. No tooling required. That's a big advantage, obviously. And then the part price hits his target at the low quantities. Lead time is very quick, and the material is this nylon 12 dyed green. Now, some of the disadvantages are that if he wanted to suddenly, if he got a big order and he wanted to scale up and it was tens of thousands of parts, he would have a hard time doing that with 3D printing. We've worked through tolerances. That's a question of like, how well does this thing fit onto that injection molded housing of the Mavic Pro, and that was something we needed to work through, but we were able to get to the point where it worked very well for him. So really a good example here of something that you're expecting capability similar to what you would get from a traditionally manufactured part, but you're using a 3D printing technology to make it happen.
Mm-hmm. I'd like to point out that there is a lot of inertia of knowledge of how you actually mold that prevents some people from thinking innovatively about how do you actually combine features and make unmoldable features. So it really takes a mindset shift going into it to challenge yourself to recognize I'm going to make some unmoldable features, and I'm okay with that because I'm trying something different.
That's true.
And a lot of management has to recognize that too, that you want to adopt a new technology, it requires new perspectives, new mind shifts, new goals and objectives of how you're actually designing.